Okay, so let's move into section 2.4. We're looking at absolute mins and maxes, and we're still going to be using the derivatives to find this. Now, first let me go over a definition. This definition says, suppose that f is a function with a domain of I. Then, f of c, remember, c is the critical value. How do you find it again? You take the first derivative, you set it equal to 0, and then you find that number. That's your c. F of c is the y value when you plug in the critical value. It is the y value when you plug it into the original function. Notice it says f of c, not f prime, but f of c. So then f of c is an absolute minimum if this y value at c is less than or equal to all the other y values for every x that's in this domain. Or f of c, again, the y value at c, the y value at the critical value, is an absolute max if this y value at c is greater than or equal to all the other y values for all the other x's in this interval I. Okay, makes sense. This y value's got to be smaller than all the other ones, or this y value has to be bigger than all the other ones in order for it to be considered an absolute min or an absolute max. Okay, mind you, it says absolute. We're not looking on just we're looking over the entire domain, I should say. So I'll leave it at that. The extreme value theorem. It says a continuous function. Remember what continuous means. There's no breaks in it. If you take your pencil and you start drawing on the graph and you never have to pick up your pencil, it's continuous. If you have to pick it up because there's an open circle or there's some kind of asymptote, then it's not continuous. So you have a continuous function f. It's defined over a closed interval. Closed means there's going to be brackets. I don't know what a and b are. I don't care what a and b are. They're just some numbers. So this continuous function defined over a closed interval must, notice the word must, it must have an absolute minimum and an absolute maximum value on this interval. Cool? I'll be right back with a couple of theorems. Okay, I'm back with two theorems as I promised. The first theorem is Theorem 8, called the max-min principle number 1. So let's see what it says. Suppose that f is a continuous function. It's defined over a closed interval. Kind of sounds like the extreme value theorem, right? Okay. To find the absolute min and maximum over the closed interval, first thing you're going to do, find the first derivative. Second thing you're going to do is determine the critical value, and you need to make certain that that critical value lies within the closed interval they gave you. If it doesn't lie within the closed interval they gave you, then you can't use it. And then lastly, you're going to evaluate the original function at the critical value and at the two endpoints, A and B. Okay? So this first principle almost sounds like that extreme value theorem that we were working with, which was the closed interval. There must be an absolute min and absolute max on that closed interval. Cool. Now, theorem number 9, called the max-min, principle number 2. So, suppose f is a function such that the first derivative exists for every x in an interval. Notice it says an interval. It doesn't say anything about the interval being closed. It's just an interval. And there's exactly one critical value in that interval. Again, it doesn't say anything about that interval being closed. It just says some interval for which the first derivative at that x equals 0. Then, f of c. So notice this is the original function, and you're plugging in c into the original function, is an absolute maximum over the interval I if the second derivative is less than 0. Okay, so you have to remember something about the second derivative being less than 0. First off, the second derivative deals with concavity. If it is less than 0, that means it concaves down. It makes sense it's an absolute max if it's concaving down. F of c, again, plugging c into the original function, is an absolute minimum over this interval I if the second derivative is greater than 0. Remember, second derivative deals with concavity. And if the second derivative is greater than 0, that means it concaves up, which explains why there's a minimum. Cool? Okay, be right back with some examples. Okay, I'm back. So, the directions ask us to find the absolute min and maximum over the indicated interval and indicate the x values at which they occur. When no interval is specified, use the interval of negative infinity to positive infinity. So let's look at problem number 1. Here's the function they've given us, and they've actually given us a closed interval, correct? Now, I have two theorems that tell me how to find the absolute minimum and absolute maximum, Theorem 8 and Theorem 9. Now, remember, the main difference between those two theorems is this. Theorem 8 deals with a closed interval. Theorem 9 doesn't say anything about a closed interval. So, in this problem, they gave me a closed interval, which means I'm going to work with Theorem 8. And Theorem 8 says that this function is continuous over this closed interval. And it is. This is a parabola, so clearly it's continuous. Now, the first thing Theorem 8 tells me to do is to find the first derivative. So that first derivative is going to be 1 minus 2x. Do you agree? The second thing Theorem 8 tells me to do is to find the critical values. So set the first derivative equal to 0. Solve it. I end up with 1/2. It also said to make certain the critical value lied in this interval. Does 1/2 lie between 0 and 2? Yes, it does. So check. I can use it. Okay? Then it tells me to evaluate the original function at the critical value and at the two endpoints. So I am going to look at x equals 0, x equaling 1/2, and x equaling 2. And I'm going to determine what the original function is at 0, what it is at 1/2, and what it is when I plug in 2. Now, gratefully, I've already done this. So, when you plug 0 into the original function, you get 5. When you plug 1/2 into the original function, you get 21/4. And when you plug 2 into the original function, you get 3. Okay, so I have 0, 5, 1/2, 21/4, and 2, 3. Now I've got to figure out what my absolute min and absolute max is. Now, by Theorem 8, the largest y value is going to be the absolute max. The smallest y value is going to be the absolute min. I think I forgot to write that down, but you get the idea. So in this case, My largest y value is 21/4. So here's how we write this. We say the absolute max is 21/4. It occurs at x equaling 1/2. Now, the smallest y value will be my absolute min. So in this case, the absolute min is 3. It occurs at x equaling 2. Pretty simple, right? Keep it that way. I'll be right back. Okay, I'm back. So we're going to look at these two problems, but let's look at problem number 2 first. Do you notice all it gave me was a function? It didn't give me any interval whatsoever. So since it didn't give me any interval, the directions said to assume that we're using the interval of all real numbers. Now, I basically start the same way because Theorem 9, which deals with no closed interval, says that you have to look at f prime of c equaling 0. Well, c is the critical value. To find the critical value, I'm going to have to take the first derivative. So, first derivative is going to be 30 minus 2x. To find the critical value, set it equal to 0. Solve. With me? Now, Theorem 9 also says there must be exactly one critical value in this interval. Well, there is only one critical value in this interval, so we're good to go. Now, I have to decide if it's going to be an absolute min or if it's going to be an absolute max. To determine this, I get to just do what I did on the last problem. I am going to take 15 and I'm going to plug it into the original problem. And when I do that, gratefully again, I've done the work, I end up with 225. So I have the y value, so forgive me, I was a little bit ahead of myself. I have the y value. I have to decide now if this is going to be an absolute min or an absolute max. By the second theorem, which was Theorem 9, to determine if it's going to be an absolute min or an absolute max, I have to look at the second derivative. And if the second derivative is less than 0, concaves down, which is max. If the second derivative is greater than 0, concaves up, which is going to be min. So let's take a look at the second derivative. Again, we're looking at the second derivative to decide if this is going to be an absolute min or an absolute max. I've got the y value. I just don't know if it's a min or absolute min or max yet. So first derivative was here. The second derivative is just going to be a -2, isn't it? Well, -2 is less than 0, isn't it? Which means it concaves which direction? Yep, concaves down. Since it concaves down, that means that 225 is an absolute, I hope you say max, and it occurs at x equaling 15. We cool? Good. Let's look at the second problem. Now, this second problem gave me an interval, but is it a closed interval? No. If they had put a bracket here, that's fine, but this part isn't closed. It goes to infinity. It's not closed. So I still need to use Theorem 9 here, which means the first thing I have to do is find the first derivative. But again, me personally, I don't want to deal with a denominator, so I am going to rewrite this as 72 times x to the negative first power. And again, I've done the work. So derivative number 1, after all is said and done, looks like this. Okay? And now you're going to take this and you're going to set it equal to 0, just like we did over here, so you can find the critical value. And I'm going to multiply everything by the denominator of x squared because I don't want it there. So I have 0 equals 2x squared minus 72. Moving the 72 over, still solving for x, dividing by 2. Taking the square root actually gives me 2 answers. It gives me a positive 6 and it gives me a negative 6, doesn't it? Okay, so here's the deal. Theorem 9 says when you're not dealing with a closed interval, which we are not, you're only allowed one critical value. Well, I have 2 critical values. But notice, my interval goes from 0 to infinity. Are both of these critical values in that interval? The answer is no. Only x equaling 6 is in that interval. So I only have one critical value in that interval, and it is going to be x equals 6. Now, I need to plug it in to the original function. So I'm going to give myself a little bit of board space here. Because I need to find the y value. So I'm going to take f of positive 6. And when I do that, that's going to give me 24. So now I have this point, 624. And I need to decide if 24 is going to be an absolute min or an absolute max. To answer that question, what do I need? I need derivative number 2. Okay, so here is my first derivative. I am going to rewrite. Don't want to deal with that denominator. And when I take derivative number 2, the 2 drops out. Power comes down. Decrease power by 1. So I end up with positive 144 over x to the 3rd. Do you agree? Now, in this particular case, I actually have an x left in my second derivative. So how am I supposed to decide if that's going to be a positive or a negative number? Well, here's how I do that. Don't I already know what x is? Don't I already know that x is actually equal to 6? Isn't that what we already decided? So when I plug 6 in to my second derivative, this is going to tell me if I end up with a positive or a negative number. And the number, I don't care if it's a fraction, is definitely greater than 0, which means it concaves which direction? Remember, second derivative deals with concavity. This concaves up, which means I have an absolute minimum, don't I? So in this particular case, and I'm going to write it over here because I have a little bit more room. Remember, here's your point, 624. So 24 is an absolute minimum, and it occurs at x equaling 6. Hope that helps. Have fun with homework.